Hi guys, in this video I'm going to talk about a new concept called equipotential surfaces. Okay. Now, as the word indicates, it's got two components, equi and potential. Equi means equal and potential is electric potential, which means it's a surface where the electric potential is the same on different points of the surface. Now, let's start with this example. So, let's say there is a charge. There's a charge, say plus Q. Right? Now, for this charge, right, what are the different points, right? What are the different points which would have the same potential? Right? Now, how would we think about this? Right? So one way to go would be to say that, okay, fine. So if you want to find different points which have the same potential, so let's think about what is the potential for a point charge. So we know that potential for a point charge is, so V is equal to KQ upon R. Right? So if this number is the same for different points, then they'll have the same potential. So now K and Q are obviously same. So if there are points which have the same R, if R is same for different points, then all those points would have the same electric potential. So same R means what? It means that if I take a sphere which has got center around, the center of which is where plus Q is, right? Then on that sphere all the points would have same distance. Let me show this. So let's say if I take a sphere here, right? Now in this sphere all the points have the same distance from here, right? So which means the potential here would be what? KQ upon R, KQ upon R, KQ upon R and so on. So all these points they constitute an equipotential surface. So I can take other spheres. I can take, let's say, a slightly larger one, right? And the same thing, right? So again, this has center here and all the points here, they would have the same potential. So this surface, this is an equipotential surface, this surface is an equipotential surface. And how many such surfaces are there for a point charge? Infinite in number, right? Okay, so now, first observation we made is that, for a point charge, right? For a point charge, equipotential surfaces are what? So they are basically concentric spheres and the center is around the, so these are concentric, right? Concentric spheres, right? And why is that? Because for a sphere, all the points would have the same value of R. Okay. Now the question is, okay, so this is for a point charge. Now, is it always a sphere? Answer is no. I mean, if you have, so instead of one point charge, you can have multiple charges. You can have a charge distribution. So it depends upon the way the charges are arranged and organized. Right? So this is one observation. Right? Now let's take another interesting example. So let us say we take a metal, right? We take a conductor. And it's an electrostatic condition, which means the charge is not flowing, right? Now, if I take some metal here, right? The surface, look at the different points on surface of the conductor, right? My question is, what would be the potential at each of these points, right? And the answer is, the potential at all the points on the surface of a conductor would be the same, right? Why is that? Because if, let's say, this point and this point, it's some two nearby points had different potential, what would happen when the potential between two points is different, right? Remember, what is electric field? Electric field is equal to, right, minus dV by dr. I'm just taking a one-dimensional case. For a three-dimensional case, we can write, del V by del x, I cap and so on, but I'm just trying to simplify this. So let's take, 2 points which are, let's say, along a straight line, and this is my x-axis, right? This point and this point, right? Just for simplicity, right? So E would be minus dV by dr, right? So which means if for a change in R, right, for a change in position, right, if there is a change in electric potential, then we would have some electric field. If there's electric field, what would happen? Then charges can flow. So let's say because a conductor has got free electrons. So if there is a field, the charge, the electrons would start flowing, and then it is no longer electrostatics, right? We're talking about current, and here we said that we're not talking about current, we're talking about electrostatics. So in electrostatics, right, all the points on the surface of a conductor would have same potential, and by the same logic, any point inside as well, right? Any point inside as well would have the would have the same potential, because again, if there are 2 points here, 1 point here, 1 point here, if there are different potential, what will happen? Charge will start flowing, right? But now since talking about surface, right? We're talking about surfaces, so I'm just saying, as a special case, right? The surface of a conductor also is an equipotential surface. Okay. Now the question is, what are the properties of equipotential surfaces? Right? So that'll be somewhat interesting. So let's look at that. So first property we notice is that so the definition is they have the same potential, and so now what are the properties? So one property which I would make a claim, and then I would like you to think about it, and then tell me if you agree or disagree, and if you agree, why, right? So one claim I'll make is that for equipotential surfaces, electric field is perpendicular to the surface, perpendicular to the equipotential surface. Equipotential surface. This is a claim I am making. I have not proved it. I have not. Maybe it's wrong. Maybe it's correct. I want you to think about this, right? And then come back with an argument as to why this is true or not true, and we'll discuss in the next video. Thank you.